In everyday life, we encounter various problems that involve counting. For example, if you have three types of vehicles, for example, you may have a car, you may have a scooter and you may have a cycle, then you can choose one of these to go to the office. I am a teacher and there are 10 topics that I have covered in the class and I have to give 5 questions. So, in how many ways I can choose the topics to make 5 questions. You might have booked tickets in say a flight and then when you go to the counter, then the seats are allocated. So, there are several ways of allocating the seat. For example, you may get an aisle seat, a window seat or a middle seat or a seat which is in the near the emergency exit. Similar type of allocation problem occurs when the seats are allocated for one person or for a family in train. In general, you are encountered with counting problems, allocation problem, arrangement problems in almost every walk of life. For example, a team of players has to be selected. So, there are say 20 probables and the team, suppose it is a cricket team. So, ultimately you may have to select only 11 full players and 1 reserved player. So, in how many ways you can choose these 12 players out of 20 players, such that 11 are to play in the main team and 1 player in the reserve. A similar kind of problem occurs, we have to form a committee for taking certain decisions, taking some courses from a list of courses. For example, at the beginning of every semester, the student has to choose say 5 courses out of a list of say 30 courses which are available. So, in how many ways he can choose. Then again there may be restrictions on the choice. For example, 2 of them may have to be compulsory and 2 of them may have to be elective courses, 1 of them may have to be lab kind of thing. So, these counting problems are encountered in almost every decision making process in day to day life. Let me tell briefly about the history of this topic. The term permutation and combination. So, that means the problems related to the counting, they were introduced probably around 6th century BC by certain Indian mathematicians. In fact, there are references in ancient texts. For example, there is a reference in Sushrut Sanhita. Let me just say it, Sushrut Sanhita. This is by Sushrut. He was ancient Indian medical professional. So, you can say one of the first, you can say doctors, and he mentions that if there are 6 different tastes, so how many combinations of these tastes can be made to produce medicines, and he gave the answer as 63. This is the number that Sushrut Sanhita mentions. Now, in modern terminology we can calculate it. In modern terminology, this is like, I will explain to you a little later. In modern terminology, this can be calculated as follows. That is, if we choose a single taste. So, a medicine with a single taste can be chosen in 6 ways. Then if you consider a medicine which is a combination of 2 tastes with a combination of 2 tastes, then that can be chosen in. Now, you have total 6 possibilities. So, the first one you can choose in 6 ways, the second one you can choose in 5 ways. However, the order in which they are chosen is not important, therefore, you can divide it by 2. So, this number becomes 15. Similarly, if we consider a medicine with a combination of 3 tastes, then that can be chosen. Now, again let us look at this 6 ways for choosing the first one, 5 ways of choosing the second one, and 4 ways of choosing the third one. Now, once again these 3 things can be in any particular order, that order does not make any difference. So, we divide by 3 into 2 into 1. So, that is equal to 20 ways. Similarly, if you consider a medicine with a combination of 4 tastes, then that can be chosen in 6 into 5 into 4 into 3 divided by 4 into 3 into 2 into 1, that is simply 15 ways. A medicine with a combination of 5 tastes can be chosen in 6 into 5 into 4 into 3 into 2 divided by 5 into 4 into 3 into 2 into 1, that is 6 ways. And a medicine with all 6 tastes. So, that means only one way. So, now if you look at the total number of ways, that is equal to 6 plus 15 plus 20 plus 15 plus 6 plus 1. So, that you can see easily 63. So, you can see here that how many combinations of 6 different tastes can be made to produce medicine. So, there are 63 ways. So, this type of calculation was known in ancient India. Then the second one is that around 3rd century BC, a Sanskrit scholar by name Pingala, he wrote Chand Sutra, and he discussed the ways of determining the number of combinations of a given number of letters, taken one at a time, taken two at a time. So, as you can understand from the name, Chand Sutra means how to write various chandas with different type of combinations. So, for example, you have these many matras, these many letters, etc. So, he used counting methods for considering various combinations of letters. Another reference is in Jain mathematicians, and they studied this topic under the name Vikalp. Around 850 AD, Jain mathematician Mahavir he has provided general formulae for permutation and combination. Around 1150 AD, mathematician Bhaskaracharya II. So, in fact, Bhaskaracharya II is well known as one of the most important ancient Indian mathematicians. It is credited that he actually compiled all the results known till that time and also added large number of his own results. So, he also in his book that is famous book called Leelavati, which was named after his daughter. So, under this topic called Ank Pash, under the topic Ank Pash, he has given various counting methods and he has actually given, you can say, the modern formulae for permutation and combination. Of course, he did not use that notations which are used today, but he actually was able to provide the general method of counting these things. There are other references in ancient China, then Greece, then there are works in ancient Arab and in Israel, which is modern Israel that time. So, you can say in Hebrew literature there is some reference to the counting techniques. The modern treatment of this subject is found in detail in the book Ars Conjectandi. It was published in 1713 and this is by Swiss mathematician Jacob Bernoulli. His timeline is 1654 to 1705. That means, the book was published posthumously and other important contributions are by Tartaglia, Pascal the French mathematician, Fermat. So, these are the famous mathematicians who actually originated the theory of probability also. uh, D. Mayer, and from the Bernoulli family itself James Bernoulli, Leibniz and Euler. All of these European mathematicians contributed in great detail to various aspects of the subject, you can say combinatorics, which has permutation and combination as one of the most important components. So, you can say that this subject is somewhat old, and in your particular course of class 11-12, we tell you the basic principles of counting. So, you can say actually there are several basic methods of counting what we actually consider. So, for example, if I say that I have say 2 cars and 3 motorcycles, and I want to choose one vehicle for transportation, then how many ways I can choose. So, naturally one will give a straight away answer that there are 2 plus 3 options. So, for example, if I have some particular event for which there are say m methods or m ways, there is another event for which there are n ways, then the total number of methods for A or B will become m plus n. So, this is the first counting principle, which is actually you can say as a layman you can think about it, because it is simply adding the number of possibilities. So, in combinatorics we call it the addition principle. The first one is the addition So, let me formally state this. Let there be m ways for an event A to occur, and let there be n ways for another event B to occur. If all ways are distinct, then the number of ways for A or B to occur is m plus n. We can express it in the modern language of sets also. Let me put it that way. If we use the language of sets, then let me put this symbol. This is called cardinality of A. Denotes the number of elements in set A, that is also called cardinality of set A. Then the addition principle states that if A and B are disjoint, the cardinality of A is m and the cardinality of B is n, then cardinality of A union B is equal to m plus n. So, basically it means that the number of ways, if you are considering several things, can be simply accumulated, that means you can add them. Now, I have written here 2 events, now you can immediately write for several number of events. Suppose I have 3 events, suppose I have 4 events, and if I have to consider the total number of ways for those events to occur, then I have to simply add the number of ways for each of them. So, this gives rise to the general addition principle. Let there be m 1 ways for an event E 1 to occur, m 2 ways for an event E 2 to occur, and so on, m k ways for an event E k to occur. Then the number of for either of E 1, E 2, E k to occur is m 1 plus m 2 plus m k. Let us consider a simple illustration here. From say Delhi to Mumbai, one can travel by air, that is 8 flights are there, by train, and 12 trains are available, and land. And in land he can use long distance bus service, or he can use a car. Then in how many ways one can travel from Delhi to Mumbai. So, naturally if you consider the event of travelling by air as event E 1, then the cardinality of E 1 is 8. If I consider the event of travelling by train from Delhi to Mumbai, then the cardinality of E 2 will be 12, and if we consider E 3 to be the event of travelling by the land route, then he can have the cardinality of E 3 as 2, because long distance bus service or car. So, if we formally define E 1 is travelling by air, then cardinality of E 1 is 8. E 2 is travelling by train, then the cardinality of E 2 is 12, and E 3 suppose I consider travelling by land, then the cardinality of E3 is 2. So, the total number of ways of travelling from Delhi to Mumbai is, so this will be cardinality of E1 union E2 union E3, which are all disjoint. So, that is cardinality of E1 plus cardinality of E2 plus cardinality of E3. So, that is equal to 8 plus 12 plus 2, that is equal to 22. So, there are total number of 22 ways of travelling from Delhi to Mumbai, if these kind of options are available. To illustrate one counting example, generally we consider some geometric shapes in which there are nested triangles or nested squares or nested rectangles, etcetera. So, I will give one problem where we have nested squares. For example, we usually consider a chessboard which is 8 by 8. So, we can have any kind of such arrangement. So, let us consider, say, how many squares are there in a 5 by 5 array. So, let me just show you by diagram to make it very clear. So, this is a 5 by 5 array and each of the cell is a square here. Okay. So, if we consider the squares in the array can be counted as E1, the set of 1 by 1 squares, E2 is the set of say 2 by 2 squares, E3 the set of 3 by 3 squares, E4 is the set of 4 by 4 squares, and E5 is the set of 5 by 5 squares. So, let us just look at it. 1 by 1 square means each individual cell is a square. Okay. So, if we look at how many of these are there. So, if we consider the cardinality of E1. So, if it is a 5 by 5 array, then total 5 square, that is 25 1 by 1 squares are there. If we consider 2 by 2 squares, that means taking 2 at a time, then it is becoming. So, if you look at the method of counting here, let us see, we can consider this as a 2 by 2 square, and then if I leave the first column and I move to the next one, then I have another 2 by 2 here. Similarly, if I leave the first two and go to the third and fourth, then again this is a 2 by 2. Then similarly, I can leave the first 3 and I can go to the fourth and fifth, then that is also a 2 by 2. So, there are actually 4 such squares, because what has happened that initially there are 5 cells, but when we are taking 2 at a time, then we have to skip 1, because starting from the first one the 2 are counted and then we can slide down. So, there are 4 such. Similarly, if we consider the width of this, so it is occupying 2 rows now. So, again we can slide down, we can consider this here from the second and third row, the same counting can be done. That means, I can consider the first one and the second one, second column and the third column and the fourth column and the fifth column. So, again it is 4 such 2 by 2 squares are there. And again if we slide down, we can consider third and fourth row. So, again 4 such squares will be there, and we consider fourth and fifth. So, again there will be 4 such squares. So, there are 4 such cases here. So, the number of 2 by 2 squares, it is actually 5 minus 1 square, that is 4 square, that is 16. So, I have written 5 minus 1 just to illustrate that since I am taking 2. So, 1 less will be there. Now, that gives a pattern here. If we consider 3 by 3 squares. So, suppose I consider 3 by 3 squares, then it will become 5 minus 2 square, that is 9. Because if I am considering 3 by 3, then I will consider first, second, third column and first, second, third row. So, that will be 1 3 by 3 square, and then if we slide along the column, that means, I consider next time second, third, fourth or fourth, fifth, third, fourth, fifth column, then there will be 3 such 3 by 3 squares in 1, 2, 3 rows. Same thing happens if I consider second, third and fourth row or third, fourth and fifth rows. So, there will be total 3 into 3. So, I am writing it in the form 5 minus 2 square, that is 9, and in a very similar way then you get E 4. The number of 4 by 4 squares is 5 minus 3 square. So, that will be simply 4, and the 5 by 5 square is 5 minus 4 square, that is 1. The 5 by 5 square, there is only 1. So, the total number is then becoming equal to that is equal to 1 plus 4 plus 9 plus 16 plus 25, that is equal to 55. So, in a 5 by 5 arrays, if we consider all the nested square cells, then there are total such 55 squares available. Let us generalize this. So, like in a chessboard you have 8 squares. So, in general if I consider an n by n array, then how many such squared cells will be there. So, let me consider this. How many squares are there in an n by n array? So, if I consider E I to be the set of I by I squares, where I can take values 1 to n. Then if we keep the same method of counting, then the number of 1 by 1 squares is simply n square. The number of 2 by 2 squares will be n minus 1 square. The number of 3 by 3 squares will be n minus 2 square, and so on. The number of n by n squares is 1. So, the total number of such squares, you can easily see it is simply 1 plus 2 square plus 3 square plus and so on up to n square. It is the sum of squares of first n natural numbers. So, we actually know the formula for that. So, the total number of squares in an n by n array is 1 plus 2 square plus 3 square plus and so on n square. So, you have done the formula for that, it is actually n into n plus 1 into 2 n plus 1 by 6. You can check, we actually solved the problem for 5, we got the answer 55. So, if we consider here n is equal to 5, then it becomes 5 into 6 into 11 divided by 6. So, this 6 cancels out, you get 5 into 11 is equal to 55, which was the answer for this one. So, as an example, we can consider in a chess board how many squares are there. For example, a chess board is an 8 by 8 square array. So, the total number of squares will be 8 into 9 into 17 by 6. So, that is equal to 204. So, in a chess board, the total number of squares, if you count, that is equal to 204. So, you can consider this as a very simple illustration of the addition principle, because what we are doing is that we are splitting the total event as a union of several events, and then we count the number of possibilities for each of those events to occur, and these events are disjoint. So, in how many ways the total number of the complete event can occur, that is simply adding all the possibilities. So, this is the first counting principle in combinatorics. The next important principle is the multiplication principle. If there are m ways of an event A to occur and there are n ways for an event B to occur, then the total number of ways for occurrence of event A followed by event B. So, you notice the difference from the language in addition principle in the multiplication principle. In the addition principle, we are saying either event A occurs or the event B occurs, etcetera. So, the what is the total number of ways? So, we simply add m plus n. In this case, both events A and B are occurring. So, we just consider it as something like this, that firstly A occurs and then B occurs, or firstly you can say B occurs or A occurs, or you just say that both A and B occur. In this case, you will have the m and n multiplied rather than added. You just think it like this. I mentioned there are 22 ways of travelling from Delhi to Mumbai. So, suppose there are another say 20 ways of travelling from Mumbai to Chennai. So, then what is the total number of ways of travelling from Delhi to Chennai via Mumbai. Then in this case we can use any of the 22 ways in the first case and any of the 20 ways in the second case. So, you can multiply. So, it becomes 440 ways. So, let me just give a brief illustration of this proof of this a theoretical proof of this multiplication principle. So, we can use the language of the set theory using the terminology of set theory. Let A be the set consisting of m elements a 1, a 2, a m. So, for an event A to occur there are m ways. So, we describe it in this particular fashion that A is a set consisting of m distinct elements a 1, a 2, a m. And similarly, let us write the set B as consisting of elements b 1, b 2, b n. Then the possible number of ways of occurrence of event A followed by event B. So, you can describe it in the form of ordered pairs. So, for example, you can say A 1 B 1. What does it mean? That means, for event A to occur, we choose the method A 1. Similarly, for the event B to occur, the occurrence is by B 1. Like I can say, for travelling from Delhi to Mumbai, we chose a flight. So, maybe the first flight, and for travelling from Mumbai to Chennai, again we choose the first flight. So, it is A 1 B 1. Now, you can consider other options. Here it can be the first flight and here it can be the second flight and so on. Here it is say first flight and here it is some other method. For example, it could be by a ship also. And then you can have the second flight from Delhi to Mumbai, then B 1, A 2, B 2 and so on, A 2, B n and so on. Finally, here you can have the last method, that is travelling by car, and here you can have the first flight and so on. So, by this arrangement you can see that the total number of elements is m into n, because we are able to arrange all the elements in an m by n array. So, the total number of ways is m into n. Once again we can write the formula using the cardinality principle here. If we want to write like this, let cardinality of A be m, the cardinality of B be n. Then what are these elements? Actually A 1 B 1, A 1 B 2 and so on. These can be considered as elements of the Cartesian product A cross B. Okay. So, A cross B is actually A 1 B 1, A 1 B 2 and so on, which we also write like this, it is an element x y such that x belongs to A, y belongs to B. So, then cardinality of A cross B is nothing but cardinality of A into cardinality of B. We can consider this as a compound event, that means, when one event is occurring and then it is followed by another event. So, it can be considered as a compound event. So, the number of ways of counting the possibilities of a compound event is nothing but you multiply for the individual events which are involved there. You can easily generalize again this to more than 2 events also. So, we have general multiplication principle. So, let there be m1 ways for an event E1 to occur, m2 ways for event E2 to occur, and so on, mk ways for event ek to occur. Then the total number of ways in which events E1, E2 and so on Ek occur in this order is m1, m2, mk. This is the product here. One point which you should note here is that, for example, in this case I considered firstly the event A and then the event B, and then I am writing the number to be mn. Suppose you exchange the order, suppose firstly I say event B and then the event A, that means, I am just redesignating my events. Now, if we apply the same logic, the answer will be n m. Now, this is not surprising, because if you consider multiplication, multiplication is commutative. Therefore, m n and n m they are same, therefore, it does not make any difference. So, therefore, in the general multiplication principle, when I am writing events E1, E2, Ek, they occur in this particular order. That means, I say firstly E1 occurs, then E2 occurs and so on, and then finally, Ek occurs. Then the number of possibilities is m1 into m2 into mk. Now, since multiplication is commutative, you will receive the same answer if I conduct the events in any other order. For example, I may firstly say E3 occurs and then maybe E7 occurs and then E1 occurs. So, in any other order if I write, still the number of elements or the number of ways will be the same. This is because if I consider the Cartesian product A cross B or B cross A, it has the same number of elements. The order of the elements may be different, because if I say B cross A, then firstly you have to say B1 then A1, that means, B1 followed by A1, and it is not the same as A1 B1, but the total number is the same. So, this is another point that needs to be mentioned. Let me just write it as a remark. In the multiplication principle, the order in which events occur does not make any difference, since multiplication is commutative and also because the cardinality of Cartesian products of sets does not depend upon the order in which sets are taken in a Cartesian product. So, this multiplication principle is actually one of the, you can say, very fundamental principle of counting. In fact, in most of the textbooks, including your CBSE textbook, this is written as the first principle. In fact, here I have added one additional thing, that is the addition principle as the first principle, but generally in the books they will start from the multiplication principle. So, anyway, I have just introduced it here. Let us look at some of the examples here. In a class of 50 students, 20 are majoring in, say, physics, 20 are majoring in chemistry, and 10 are majoring in mathematics. So, in how many ways we can choose a representative from each group. So, we want to have a 3 representatives in such a way that one is from physics, one is from chemistry, and one is from mathematics. So, now this is a very simple thing. If we apply the multiplication principle, in that case, if I consider this first one, that means the students majoring in physics. So, the representatives from there. So, he can be any of the 20 students. So, the total number of ways will be 20. So, in that way, if I write for physics, chemistry and mathematics, then if we use the notation here, let me give you a systematic presentation here. So, let us consider E1, that choosing a representative from students majoring in physics. Similarly, if I consider E2 as the representative majoring in chemistry, and E3 is the choosing a representative from students majoring in mathematics. So, then if I consider cardinality of E1, that is 20, cardinality of E2, that is 20, and the cardinality of E3, that is equal to 10. and therefore, now the cardinality of E 1 cross E 2 cross E 3, that is nothing but 20 into 20 into 10, that is equal to 4000. So, there are 4000 different ways of choosing 3 representatives, one from each group. Let us consider a ternary sequence. So, a ternary sequence consists of digits say 0, 1 and 2. Okay. Like a binary sequence consists of 0, 1, similarly, a ternary sequence consists of digits 0, 1, 2. So, how many 5-digit ternary sequences can be formed? So, now you see I am considering a 5-digit ternary sequence. So, these are 5 places here. In the first place, I can put either of 0, 1 or 2. That means, the first place can be filled up in 3 different ways. In the second place also I can put either of 0, 1, 2. In the third place also I can put either of 0, 1, 2. In the fourth place and in the fifth place also the same logic will be repeated. So, in each position we can place either of 0, 1 or 2. So, the number of ways of filling each position is 3. Total number of positions is 5. So, by the multiplication principle, in short I can use MP. The total number of such ternary sequences is 3 into 3 into 3 into 3, that is 3 to the power 5, that is 243. I will continue in the following lecture on this further examples of multiplication principle, and then we will talk about arrangements, that is permutations and combinations.